Hello, everyone, and welcome to Talk Nerdy. Today is Monday, April 6th, 2020, and I'm the host of the show, Cara Santa Maria. Now, this week, we're going to be having a really great chat with an astrobiologist who works at NASA's Jet Propulsion Laboratory. But before we do that, I want to thank those of you who have made Talk Nerdy possible this week. Remember, Talk Nerdy is and will always be 100% free to download, and that's because of support from listeners just like you. If you want to pledge your support, you can go to patreon.com/talknerdy. You can visit talknerdymerch.com to buy some merch to support the show. Or you can rate and review on iTunes, on Stitcher, on, I guess it's called Apple Podcasts now, on Google Podcasts, anywhere else that you listen to the show. That's probably one of the best ways that you can support the show, and it don't cost you nothing. I know everybody is in a really difficult place financially right now. The globe is experiencing unprecedented pressures. And of course, I was a little bit on autopilot when I started recording and said the same thing I always say. But obviously, if you were in a position where your finances are being strained, not only do I urge you not to support the show, but also if you are a longtime patron of the show, please do what you need to do to make sure that you're in a good place right now, because I know it's tough out there for everybody. This week's top supporters on Patreon include Michael Gaucher, Christopher Pitts, Mary Neva, Pasquale Gelate, Ulrika Hagman, Dudas Infinitas, Brian Holden, Daniel Lang, and David J. E. Smith. Thank you all so very much. And to everybody else who, comes back week after week to listen to the show. All right. Let's dive right in. Okay, so this week I had the opportunity to sit down, not physically with, but remotely with, which is kind of funny because he only lives 2 weeks away from me. 2 weeks, that doesn't make sense. 2 blocks away from me. Mixing up my time and space here. He is a planetary scientist and astrobiologist at NASA's Jet Propulsion Laboratory in Pasadena, California. He's the director of JPL's Ocean Worlds Lab. He's the pre-project scientist for NASA's Europa lander mission concept. And he's a co-investigator on the Clipper mission, the Dragonfly mission, and the investigation scientist for the Sherlock instrument on Mars 2020. Wow, that's a lot. His name is Dr. Kevin Hand, and I should be clear that his views in talking to me on the show are not representative of the views of NASA, the Jet Propulsion Laboratory, Caltech, or the federal government, of course. And I wanted to have him on the show because he has a brand new book out, and it's called Alien Oceans: The Search for Life in the Depths of Space. Let me see what day the actual book is. I think it's available. Oh, yeah. April 7th. That's amazing. So today's April 6th, if you're listening to this on drop day. So it's on pre-order right now, and it's available to ship tomorrow if you're listening to this the first day. Otherwise, it's already available. So go and grab it online. I know you'll want to after you listen to the episode. So guys, without any further ado, here he is, Dr. Kevin Hand. Well, Kevin, thank you so much for joining me today.
My pleasure. Good to be here, or wherever we are.
I know that's the weird thing about life in the time of COVID-19 is that we literally live blocks away from each other, but we are doing this recording remotely.
It's got to be done.
Yeah, we got to be good about this. There's a chance, I don't think I was actually exposed, but there's a chance that I could have been exposed because somebody I know is sick. And it was 2 weeks ago when I last saw them, but just out of, an abundance of caution, I think it's a good idea to do this. And we're not saying social distancing now, physically distance, because we are in this recording, aren't we?
I guess that's right. Yeah, we'll see how these various terms evolve.
Yeah, exactly. So I'm really excited to have you on the show today because you have written a new book. But of course, there's so much more that I cannot believe we've never done this before. I've had this podcast for 6 years now.
we've been talking about doing this for just about as long. So it's
Yeah.
good to finally do this while COVID-19 is taking over the planet.
Yeah, why not? We got time now. So, your new book is called Alien Oceans: The Search for Life in the Depths of Space. And there's a lot to unpack, even just in that title. So, I kind of want to start by going a little bit back to the beginning, maybe not the beginning, but I'd love to know, as an astrobiologist, like, number one, I've had one astrobiologist on the show before, a gentleman by the name of Mike Lee. And we talked a little bit about what astrobiology is, but I would love to hear, A, what is your take on what it means to do astrobiology, or to I don't know, hold that title of astrobiologist? And B, what kind of education did you get in order to find yourself in this position?
Yeah. So astrobiology is the study of the living universe. And what I mean by that is that we know that at least part of our universe has biology as a process, and that amazing little corner of the universe is our planet Earth. And so, in astrobiology, our goal is to search for life beyond Earth and see whether or not the living universe extends beyond our home planet. But coupled with that, we're also incredibly interested in the origin of life on Earth, the evolution of life on Earth, and the future of life on Earth, looking at biology, looking at life as a planetary process. And so, we can sum up astrobiology as the study of the living universe.
Interesting. So I almost see some parallels that are similar to those in my friends and colleagues who are planetary scientists, where some of them actually study Earth and Earth's processes, but then some of them study the moon, or they study Jupiter, or they study Pluto. But they often kind of will parallel things that are happening on Earth to things that are happening on other planets.
Exactly. So, a great example that I love to use is James Lovelock. Lovelock wrote, of course, the classical book Gaia, and pondered the role of life on Earth and planets, and how there's uh, how there can be feedback mechanisms. And Lovelock first started pondering Gaia when he was at JPL in the 70s, thinking about Mars and Venus and the Earth and what makes them habitable or not habitable. And so, planetary science is about all of these different things. How do solar systems form? How do planets form? How do they evolve? How do atmospheres work? How do plate tectonics work? What's the rock cycle on Earth and other worlds? And so, for much of planetary science, for much of the history of our exploration of our solar system and beyond, we've really focused the on three of the four major branches of science. We focused on physics questions, of gravity. How do planets form and arrive at the size and density that they are? The chemistry, what constitutes solar systems, what constitutes planets. Geology, how do they, does plate tectonics work? Do these other worlds have volcanoes, and if so, why? So we've looked at physics, chemistry, and geology beyond Earth, but we have yet to make the leap of seeing whether or not biology actually works beyond Earth. And that really, at the heart of it, is what it inspires me and many of my colleagues in this exploration, this endeavor of astrobiology. Does biology work beyond Earth? And it's exciting because for the first time in the history of humanity, we can actually ask that question, and in so doing, answer that primordial, age-old question of, are we alone?
Geez. So, like, in so many ways, the work that you do, and that you've really dedicated your life to, is sort of one of these final open frontiers. But in order to get where you are right now, you must have had to really have a lot of, like, breadth in your training. You know, we the joke, right, is that when you start in as an academic, you know a little about a whole lot, and then as you become more specialized, you know a whole lot about very little. But you still have to know a whole lot about a lot.
Yeah, and and so uh, it's a fantastic and wonderful field to go into, in part because astrobiology can be kind of this umbrella that brings together a lot of the best and brightest in specific disciplines. And so my sort of academic genealogy is physics and astronomy. I did also study psychology, and we can get into that a little bit. That had to do with the search for extraterrestrial intelligence. Um, and then I studied robotics and mechanical engineering. So when it comes to my kind of academic genealogy, in undergrad I studied physics and astronomy, and I also got a double major in psychology, and that was largely motivated by an interest in extrasensory perception and the connection to communicating with extraterrestrial intelligence. And we can get
Oh,
into that later
wow.
if you want.
Wait, so you just to kind of interject, you knew that this was sort of where you wanted to go even as an undergraduate?
Oh yeah, I was obsessed with aliens as a kid.
Nice.
Carl Sagan's Cosmos, and just growing up under the clear night skies of Vermont, where I grew up. Yeah, I was building model rockets with my friends and stuff, and
Oh,
so
I
I've
love
been
that.
captivated by aliens since I was a young kid. I saw ET and wanted to go into the woods behind our house and find find an alien spaceship, and you know,
Damn it.
and it never.
Didn't quite work out that way.
That's right. Uh, yeah, I can keep the dream alive, but
Yeah, seriously. You never know. You
yeah.
never know.
um, so yeah, I went into college. I went into physics and astronomy with that goal, and uh, interestingly, back then, and this is still largely the case, the search for life is not always embraced by professors and various academics, and uh, there's some good intention in that, but there's also, I think, some failure to recognize the potential revolution that we stand to initiate with a rigorous exploration of the solar system and a search for life beyond Earth. So, yeah, when I was studying physics, a number of my professors said, "Oh, don't go into the search for life elsewhere. You're better off studying fundamental physics and doing X, Y, or Z." And I think they were definitely looking out for me. The search for life beyond Earth is a risky field, and there are those who say, it's a science without a subject, etc. But those critics are flawed logically. History, the history of science, is full of examples of um, studying concepts that don't yet have full evidence. Gravity waves is the most recent one that's been a tremendously powerful example. Gravity waves have been theorized for many, many decades, and it's just within the past few years that we finally have confirmation that they exist.
And even if something, doesn't turn out right away or ultimately at all, it doesn't mean that it's all for naught. I have a lot of friends who are like string theorists, and they're like, we don't know. Yeah, it's just an idea. Like, it's probably not even real. Like, all of them are like, yeah, it's probably not even a thing. But it still contributes to our understanding of so many things. I mean, you learn so much through these endeavors.
Right. And scientifically, and from the standpoint of the scientific method, what's most critical is that you can formulate an hypothesis about the discovery that you think might be possible. And so with gravity waves, obviously, from Einstein on up, the theory was well founded in terms of the prediction that we should be able to find gravity waves. We are now at a point with biology where we can make some predictions based on our understanding of life on Earth about what environments beyond Earth could be habitable and what environments may or may not have given rise to life. Now, there are still many, many unanswered questions. We do not know much about the exact environment under which life on Earth arose. Did it arise in tide pools on sunbathed shores of ancient continents, or did it arise in the minerals around a deep sea hydrothermal vent? We just don't know, but we can put forth a viable hypothesis that conditions similar to those for which we think the origin of life arose and which then sustained life, those conditions likely exist on planets and moons beyond Earth. And usually when people think about life beyond Earth, they think of our nearest neighbor, Mars. And Mars is, in fact, the most sort of Earth-like world that in the past had liquid water on its surface, ancient shores and continents, and an atmosphere and sunlight bathing that ancient ocean. If we've learned anything about habitability in the past 55 plus years of solar system exploration, if we've learned anything that has truly kind of changed the paradigm of habitability, it's that oceans, alien oceans, oceans of liquid water exist beneath the icy shells of many moons of the outer solar system. These are moons like Europa, which orbits Jupiter, Enceladus, which orbits Saturn, and Titan, which also orbits Saturn.
And, we think about this idea of the kind of Goldilocks zone, this idea that you mentioned Mars, or when we're looking at exoplanets, right? Planets around other stars, not our sun. We think about, oh, it has to be this distance and it has to have this kind of temperature and it has to have, an atmosphere and, all of these different ideas of what we think needs to support life. But in some ways, the idea of life under a frozen ocean sort of break some of those original paradigms.
That's right. It's a new Goldilocks. And so the traditional habitable zone, the habitable zone that astronomers and planetary scientists worked to develop from the 60s, 70s on up to now, was one wherein the energy to maintain and sustain liquid water on the surface of a planet came from your parent star. In our case, of course, that's the sun. And we have this kind of Goldilocks scenario, and this kind of ties back to James Lovelock, where the Earth is at just the right distance to have enough energy from our sun, such that it can maintain liquid water on the surface.
And so, when you say energy, you mean like in the form of heat and light?
Yeah, heat and light, exactly. So across the spectrum of photons that we get from the sun, everything from the UV to the longer wavelength stuff, ultimately eventually gets turned into heat, and some of that can help keep the surface temperature of the Earth high enough to sustain our liquid water oceans. Now there's many layers in there. Earth has an important greenhouse effect that results just from the water in our atmosphere that helps keep our temperature high enough for liquid water on the surface. But the broad brushstroke is that in this kind of traditional Goldilocks scenario, this traditional habitable zone, Venus is too close and too hot, Mars is too far away and too cold, and the Earth is at just the right distance from the sun to be in that Goldilocks zone for habitability. But there's a new Goldilocks in town, and it's one wherein the energy for maintaining liquid water comes not from the energy from your star, but rather from tidal energy, from tidal dissipation, from the tugging and pulling, the stretching, the mechanical energy that moons like Europa experience as they orbit their giant planets. And in the case of Europa, it's orbiting Jupiter, and Jupiter is 318 times as massive as the Earth. And so, just think about the tides that we experience with our moon. And now imagine you're on Europa, and Europa is about the size of Earth's moon.
Oh,
Uh,
really?
yeah, it's
Oh, wow. Yeah,
yeah,
that's a huge differential.
right, exactly. And so there are some predictions that indicate that on Europa, as it goes around Jupiter, the surface rises and falls by about 30 meters or nearly 100 feet. That's a
Holy
tremendous
crap.
ride of the tides.
Yeah.
And so Europa's just sort of the canonical and sort of the first and perhaps most well developed case of this new Goldilocks. Enceladus and Titan, and to some extent Ganymede and Callisto um, fall into this category. And then we've got worlds like Pluto, where there's not really much in the way of tidal dissipation, but there you've got, we think, enough of the heavier elements, enough of the elements that undergo radiogenic decay, so as to supply some internal heating within the rocks of Pluto to maintain a liquid water ocean with perhaps some ammonia that serves as an antifreeze. And
No
that's
way. So
also,
it's almost like a little furnace, like a nuclear furnace inside of Pluto?
yeah, and the radiogenic elements exist in a lot of these worlds, and that's another aspect of this kind of new Goldilocks. So, okay, we covered tides. Let's cover kind of other dimensions on these or other axes in this parameter space. So, um, uh, let's cover water, and then we'll go to the heavier elements. Um, So with worlds like Europa and Enceladus, we think the predominant form of energy is coming from tides, but they too have some radiogenic decay, and that comes from the heavier elements. But you might first say, well, how the heck do these worlds have enough water to even have an ocean to begin with? And there, it's kind of a funny story. Life on Earth is a bit confusing because the Earth has really kind of a lot more water than it technically should. Um, the inner solar system, we've got all these rocky planets. Mercury, Venus, Earth, Mars. Earth is really the standout case there, where we've got a lot more water than these other worlds. And when you kind of take a step back and look at the evolution of the solar system, it kind of makes sense. Think about the sun as a campfire, and you're sitting around the campfire. Whatever's closest to the campfire is going to get baked out. It's going to get dehydrated. It's going to get too hot, and it's going to lose whatever water and other volatiles it once had. And that is the story of the inner solar system. A lot of the volatiles, like water, were lost due to heating from the sun. And so on Earth, we think that a fair amount of Earth's water, perhaps as much as 50%, was delivered after Earth formed, and it was delivered by ice-rich comets and perhaps asteroids that also had or have water ice, so-called main belt comets. And so, even though the evidence speaks to the contrary, um, Earth should actually be a bad place for life. Earth has a bit more water and coupled with that, a bit more carbon than initial formation models for the solar system really permit. Meanwhile, yeah. So and then So that brings us to the outer solar system. As you go out in the solar system, things get colder and colder. And what that means for various molecules, and in particular small molecules like water and methane and ammonia and sulfide and various things, you eventually get to a point outward in the solar system where it's cold enough such that those molecules start to stick together and solidify and form ice grains and essentially condensations of these various compounds. And so, with Europa and the moons of Jupiter, and Enceladus and Titan and the moons of Saturn, and so on and so forth, those worlds actually formed rich with the light elements that life needs. They formed with quite an abundance of the carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur that serve as the key elements for life. And so, that hydrogen and oxygen combines to form water, and that's why Europa, for example, has a global liquid water ocean of some 100 kilometers or 60 miles in depth.
So how far out do these things have to go, or at what point is it so cold that there isn't even liquid water that can be sustained underneath the ice water? Like, is there anything that's frozen solid? Like, is Pluto frozen solid?
So this brings us to another axis in that kind of Goldilocks of habitability. And I go through this quite a bit in the book in terms of like the various elements. So I just covered the light elements that life needs. Then when we move further down and along the periodic table and think about the heavy elements that life actually needs to do the business of life, but also those heavier elements that help with radiogenic heating, we can look in the outer reaches of the solar system and look at the density of these worlds. And here, density serves as a proxy for how much rock content, how much of the heavier elements do these worlds have, and then ultimately how much radiogenic heating could they have. So at Europa, we're talking about a bulk density of Europa that is about 3 grams per cubic centimeter, a bit more than that. And that means that Europa basically has a lot of rock in its interior. Meanwhile, Mimas, one of the small moons of Saturn, which could potentially have an ocean. We don't have very good evidence, but there's a few whiffs of data that indicate that Mimas might have liquid water. But Mimas has a density that's close to 1 gram per cubic centimeter. Why is that interesting? Well, water, ice, has a density of 1 gram per cubic centimeter. And so if Mimas's bulk density is about that of ice, that means that even if Mimas has an ocean beneath its surface, a liquid water ocean, that liquid water is not going to have much interaction with rocks. And that's interesting from 2 perspectives. One is that there's not going to be much of those heavier elements for radiogenic decay. And it means that if Mimas were to have an ocean, the seafloor of that ocean is probably not going to have much in the way of hydrothermal vents and other interesting geochemistry that could help serve as a site for the origin of life and a site that maintains habitable environments. Now, Pluto, though, Pluto apparently, Pluto's density could support, it indicates that it does have a decent amount of rock in its interior. And so Pluto's ocean might have some rocks down at the base, though it could also have a bunch of weird types of ice.
Huh. So there might be like at least a tiny bit of water under the ice, but above the rock on Pluto.
That's right.
So tell me, this is kind of a stupid question, but I know very little about earth science and geology. If there is rock interior, in a world, does that also mean that there's like a core? like a molten core or like some sort of different state of matter underneath that rock?
So it's absolutely not a stupid question. It's one of sort of the key questions when it comes to planetary science and and the evolution of planets. And the fancy word that we use to describe that is differentiation. So when a planet forms, did it accrete enough energy? Did it accrete enough material so as to set up a bit of a density gradient, or a gravity gradient, such that the heavier elements migrate inward over time and eventually have enough heat and pressure so as to differentiate into a core and a mantle, and then a lithosphere, and then perhaps an outer um, ocean and ice shell and all that stuff. So this aspect of differentiation is key to understanding planets like the Earth and many of these moons of the outer solar system.
And so is that required for things like volcanism or for things like hydrothermic vents?
Yeah, again, it's a great question, and there's two. Europa and Enceladus serve as good kind of archetypes in this. Um, Europa is, as I mentioned, about the size of our moon, and it's big enough and it's old enough, and during accretion, we think it had enough energy where Europa did differentiate. So our current models for Europa, and these models are based on data collected from the flybys of the Galileo spacecraft back in the 1990s and 2000s, where by carefully monitoring the Galileo spacecraft, you could get the moment of inertia, the sort of gravity well structure of Europa, and from that, the gravity team on the Galileo spacecraft was able to figure out that Europa most likely has a core, an iron or iron sulfur core. Over that is a silicate, a rocky mantle. And then over that is this layer of unit density material, which is coupled with some other lines of evidence, best fit by a layer of water, some of which is in ice and some of which is in liquid form. Meanwhile, at Enceladus, uh, for the most part, we think that Enceladus is not yet differentiated, and it probably will not differentiate. Enceladus is only 500 kilometers in diameter, or 300 miles. Um, yeah, that's about the distance from Chicago to Cleveland. And so Enceladus is this beautiful, adorable little moon that is surprising everybody with the fact that it's got this subsurface liquid water ocean, and to some extent, it causes planetary scientists and astrobiologists like myself to just scratch our heads, because Enceladus has no business doing what it's doing. Enceladus has no business having an ocean, just strictly based on our sort of the strict theory of planet and moon formation, and how big a world is and what its density is, etc. But that's, of course, why we do this exploration. You get out there, and the tidal energy interaction with Saturn is pumping a lot of energy into Enceladus, and that's helping to maintain this subsurface liquid water ocean.
But doesn't Enceladus, like Europa, also have like jets, like water spewing out past the surface? How does that happen?
Yeah. So so to be clear, we definitively know of these plumes, these jets of oceanic water erupting out into space on Enceladus. For Europa, we don't yet know for certain whether or not it has plumes of water erupting out into space. There are a
What's your take on it?
number.
Do you think that they do? Do you think that it does?
Well, it's complicated. The Galileo spacecraft did not see any plumes erupting out of fractures on Europa. Now, there's a huge asterisk on that because um, the Galileo spacecraft was not able to do that much in terms of global um, imagery at high resolution. And so it's entirely possible that we could have missed any new fractures or plumes and jets erupting out into space. And my colleague Cynthia Phillips at the Jet Propulsion Laboratory long ago took a look at the available imagery, comparing not just the Galileo data with itself, but also looking at Voyager data. And she found that no plumes were visible in the available data set. But that data set, again, is quite limited. Meanwhile, when Cassini got out to Saturn and started flying by Enceladus, the magnetometer on board, the sort of fancy compass on board, detected an anomaly, and the camera took a look and saw these plumes just jetting out into space. So at Enceladus, these plumes were easy to see. But there's another layer to the story here. Enceladus, by merit of being this tiny low gravity moon, allows its jets, its plumes, to erupt out into space for many hundreds of kilometers. Yeah, so the plumes of Enceladus erupt out into space almost for the full diameter of Enceladus itself.
Yeah,
So
so that would be a little easier to see.
that's right. Meanwhile, at Europa, the gravity there and the modeling there predicted that we shouldn't expect plumes to erupt much beyond many tens of kilometers or perhaps as much as 200 kilometers. Uh,
Oh, okay. So I'm finally putting it together. So that the activity of these plumes is not tied to any sort of volatility deep within the moon. It's actually tied to the physical gravity that's being exerted on it, like the tidal forces from the planet.
yes, although there's still a lot we need to study and understand about that. On Enceladus, there's some interesting work being done on do the fractures open and close with each tidal cycle, and there are some who think it does and some who think it doesn't. But the
But
key
it's not
thing,
like volcanic and like it's not, like Old Faithful or something like that.
that's right. And so you may have noticed that I've avoided the term geyser.
Yeah.
And that's because in physics, geyser refers to a very specific set of conditions that give rise to something like Old Faithful. And I've also avoided the term volcanism or cryovolcanism because there again, when you think about volcanoes, there's a different kind of magmatic interaction. And Io, the innermost large moon of Jupiter, Europa's inner neighbor, is a great example of volcanoes working in dramatic fashion in our solar system and being driven by tidal dissipation. So, we know that tides can drive volcanoes. On Europa and Enceladus, it would be more a matter of um, you've got liquid water in the subsurface. Now you open up a fracture, and that fracture may connect all the way to an ocean below, or it may connect to a pocket of liquid water. And I think what's happening, as do many of my colleagues, is that you essentially get uh, boiling of that liquid water driving the plumes. And so it's kind of weird for us to think about boiling happening in something that's essentially at freezing temperature, right? But the thing is that the boiling point changes depending on what pressure you're at. Anybody who's tried to cook a meal up high on a mountain knows that it's you'll get to boiling faster, but the water won't be as hot, and so you actually have to keep things cooking for longer. At Enceladus, we think the fractures in its ice shell do connect to the ocean below, and so the fractures cause some of that liquid water to be exposed um, through the fracture to the vacuum of space, and that drives kind of this bubbling, boiling, uh, um, energy that drives the plumes.
Man,
Yeah,
physics and chemistry are cool.
yeah, and so that
That's
this
so crazy.
this may also be happening on Europa, but if it was happening, it would be harder to find. Now, a number of teams, one of which I'm on, led by Bill Sparks at the SETI Institute and formerly of the Space Science Telescope Institute, we've used Hubble, the Hubble Space Telescope, to look for plumes on Europa. Um, and we think we've got some compelling evidence. I wouldn't say that it's a closed case, but we're going to get back out to Europa within the next decade with a flyby mission called Europa Clipper, and that will give us a tremendously exciting close-up view of Europa and tell us once and for all whether or not there are plumes erupting out into space, and it'll also help us understand and assess the habitability of Europa.
Very cool. So Clipper is going to have obviously a lot of science instruments, but also it's going to have some pretty amazing actual visual cameras so that you can capture some of that data.
That's right. It's got a narrow angle camera and a wide angle camera, PI'd by my friend and colleague Zibby Turtle out of the Applied Physics Lab. And then it's got two mass spectrometers on it, one of which I'm the co-I on, a dust analyzer. And so if there are plumes erupting out of Europa, the Clipper mission, the Clipper spacecraft, will be able to actually taste those plumes in a way similar to what Cassini did out at Enceladus. But now on the Clipper mission, we've actually got more advanced instrumentation, and we'll be able to do even more detailed science on anything that we're able to taste coming up out into space out of Europa.
Oh my God, I love that. Okay, so we've been spending a fair amount of time just talking about whether or not another world could support water. And then we still have to bridge that really big gap between water and life because those, there's a leap there, right? Like we know that water at least seems to be necessary to support life. And that's based on, my guess is what we know about our own planet because we have an N of 1. And we've just got to kind of extrapolate out from that. But how do you even get from water to life? I mean, my guess is we don't really know.
Right, and so so you touched on a critical point there, and this comes back to some of the earlier discussion we had about hypotheses. And when it comes to sort of the biology hypothesis, if you bring together liquid water, the elements that serve as the building blocks for life, some form of energy that can power life, and some sort of catalytic surface that will help serve as the template for the origin of life, will you then get life itself? That is sort of what I like to frame as the biology hypothesis. Based on a study of life on Earth, we can put forth an hypothesis like that because we understand water-based, carbon-based life, where water is the solvent and carbon is the primary element that serves as the building block. So when it comes to building spacecraft that can search for life beyond Earth, that is hypothesis-driven science, searching for water and carbon-based life. Now,
So those
Mother
are kind of the
Nature,
two things that we focus on so far.
water and carbon. Yeah, follow the
Yeah.
water has
Okay.
long been NASA's mantra in the search for life. And then coupled with that, we can say follow the carbon, follow the nitrogen, follow the phosphorus, follow the energy. There are lots of different teams that are funded by NASA to look at these different dimensions and kind of the parameter space of habitability to kind of assess our hypotheses uh, for what makes life possible. And a lot of that is focused on life as we know it, water and carbon-based life. But as you alluded to, Mother Nature doesn't give a darn what we want to look for or what we think might be the best game in town. Mother Nature might have all sorts of weird life out there.
Yeah.
And it could be based on a different solvent or a different subunit that forms the basis of the polymer. And in my book, Alien Oceans, I get into this and I refer to it as the periodic table for life, or the great tree of life. Part of what excites me about the search for life beyond Earth is the search for extant life, life that's alive today, and life that we could then study to understand what makes it tick. Does it depend on the same biochemistry as us? Does it depend on DNA, RNA, proteins, and ATP? Or is there another game in town? Is there a different way to get the business of life done?
And you mean potentially beyond Earth, or even within our own systems here on our planet?
Well, so there is the potential that some sort of shadow biosphere is many of my colleagues in the field like to refer to it. There is the potential that a shadow biosphere on a different biochemistry exists on Earth. We cannot rule that out.
But so far, we haven't found any evidence.
So far, we haven't
support
found
that.
it. And frankly, I think what makes Earth so beautiful in part biologically is also some of what confounds our efforts to search for these things like a shadow biosphere and to understand the true limits of life, because it's hard to actually go any place on planet Earth where you cannot find even a single microbe. So
True. And pretty much the system that all of life, we think that all of life emerged from something, from a beginning. And pretty much that system, even if it did it multiple times over, that system seems to be conserved. Like it seems to be the same everywhere.
That's right. It outcompeted. If there were different origins of life, separate origins that perhaps tried a different biochemistry, they clearly got outcompeted by what was likely an RNA molecule that dominated during that epic, perhaps 3.8 billion years ago or so, of an RNA world where the RNA molecule served as both the information molecule and the molecule that really organized the building of life. And that RNA world stamped out perhaps any other primordial trees of life. And then that RNA world emerged into what's now our DNA-based tree of life.
Mm-hmm. And so, like, we even had, I remember now it was like several years ago, the kind of big stink about potentially finding, what was it, like arsenic-based life, or I can't remember. But then, of course, it didn't pan out.
Yeah, I'm not even going to touch that one.
Yeah. And those are the kinds of things that I think I get the excitement around it and the interest around it, because it could open up so much. But of course, like, what works on planet Earth seems to work on planet Earth, and it seems to work really damn well. And I mean, I'd love to hear from you, like, how many of your colleagues, and what is the kind of the dominant view in the field that formula is very likely the same formula for what potentially would be beyond planet Earth?
Well, so the water and carbon-based life, to quote Carl Sagan, he used to say that he was a carbon chauvinist, and he was a carbon chauvinist for good reason. In that, when you look at the periodic table and look at carbon's ability to bond with itself and with other elements, it gives rise to stable molecules that under a variety of temperature and pressure conditions are stable enough that processes can operate on them, but they're not overly stable so as to be incapable of breaking bonds and reassembling.
Right, it has to be dynamic as well,
right,
but not too dynamic.
That's exactly right. And so, so silicon is a great example. I often get asked, well, could you have silicon-based life? And why not consider that? And I would love to, but under pretty typical planetary conditions, silicon does a great job, but and it's very abundant. But it's very abundant, and it does a great job in forming crystals. It forms the silicate tetrahedrons that are, that we are standing on, that we are dependent on the surface of the Earth as our crust, as our lithosphere and mantle. And so silicon is incredibly successful at forming really strong structures that are actually hard to break unless you get to, molten lava kind of temperatures. Whereas carbon, you can reside in this kind of dissolve in water and form solids, and have water loving ends and water phobic ends to your molecules that can help give rise to the membranes and many of the other key molecules that form the structures of life.
I remember this from biology.
Yeah,
Phospholipid bilayers. Yay. I
exactly.
learned something.
Exactly. Yeah. Yeah, exactly.
And that's the only way for systems. Well, not the way we know for systems to form, right? For cells to not burst open, for individual units to be able to have organization, because otherwise there would be no inside versus outside, and then there would be no all the things that we need, right? No transferring of energy and everything that kind of comes from that.
That's right. And there again, we almost are certainly limited by our human creativity and our ability to think outside the box. Titan, this beautiful moon of Saturn, is a great example of an ocean world, an alien ocean that we are going to. I'm a co-I on the Dragonfly mission, and this mission will get out to Titan and explore its surface in the mid 2030s. And Titan's got an ocean beneath its icy crust, but it also has these beautiful and bizarre liquid methane and some ethane lakes and seas. And who knows? Maybe Mother Nature has got some form of weird life, some alien biology that's operating with methane as the solvent, which would be a non-polar solvent in contrast to water, which is a polar solvent. There could potentially be a methane solvent-based form of life that goes well beyond our understanding of a lot of the biochemistry that drives life as we know it.
Yeah.
And that I
Okay.
would classify as true discovery-driven science. Coming back to this discussion of hypothesis-driven science.
So sort of bottom up versus top down.
Right. And so when we do exploration, be it on Earth in any endeavor, or with NASA or the European Space Agency or the Japanese Space Agency, all the different missions that we're sending out into space, we generally try to have missions that are rooted in well-vetted hypotheses and science questions and goals that can definitely be addressed. But we try to leave the door open to new discoveries of which we can barely even conceive of. And so life in the lakes of Titan is a great example of that. I cannot formulate a really solid hypothesis for how life would work in the lakes and seas of liquid methane of Titan. But the Dragonfly mission will have the capability to search for interesting chemistry on the surface that could perhaps give us some indication of signs of life on that alien world.
Oh, I love this. I love that we're able to sit here and talk not just about content of the work, but also about the process of the work, because I think that's so important, and it's something that we don't often get exposed to, kind of in the general public, when we're learning about new findings or discoveries or areas of interest in different fields of science. We're so often looking at either incremental advances or rarely big discoveries, but it's nice to be able to talk about how you figure out what you figure out, and how that informs the science as you iterate. I think that's a cool aspect of the conversation that we're having. But of course, I want to get back a little bit to this idea of life itself, whether we're talking about the kind of earthbound parameters or beyond, and maybe get a little bit philosophical. I got to ask you, first of all, the hard question, which is, what is life? and And then, of course, I mean, we've been sort of leading up to it at this point, but like, is there a situation that you can think of where we would potentially come across life and not even know that it was alive?
Yeah, two great questions that are at the heart of what I do and many of my colleagues do. What is life? And this is going to sound very sort of unromantic, but life is a process that alleviates chemical disequilibrium in the environment. Life is a layer on top of geology. Now, here I'm excluding, say, AI. I'm excluding advanced, robots from a very advanced civilization, um, and I'm constraining it just to sort of life as we know it. And to a large extent, this does apply to those other forms, but really, what life does for the universe, because at the end of the day, uh, everything that happens in the universe has to answer to the universe and the physics of the universe. And what the universe wants to do, I hate to tell you, it wants to get to that ultimate heat death and maximize entropy.
Yeah.
And
So it
so
wants for shit to just start to break down or start to disorganize. It goes from an organized state to a disorganized state.
that's right. And life helps the universe do that at a rate that is faster than what would occur in the universe without life.
Really? That's so funny because I feel like a lot of times when people talk about life, they talk about it almost being like entropy averse, that it's something like, I know, right? That like, oh no, but we reproduce and we have like these systems that are closed and in a way we're not, but we also die and we also get sick and everything goes to shit.
Yes, and so therein lies part of the problem, because we do have a certain observer bias in how we think about life and biology as a process.
Yeah, that's an understatement to say the
Right. So we're happy to look at the rock cycle and plate tectonics and volcanoos and say, oh, look at that. That's planet Earth just dissipating energy from accretion and radiogenic decay and all this stuff that, planet Earth is just trying to outgas a bunch of this energy that it accumulated. But when it comes to biology, we get very precious, and we say, "Oh, but look at us! We're so we organize things, we bring things together, et cetera, et cetera." And I would love to someday be proved wrong, and perhaps there's a bunch of stuff that we don't yet know about the fundamental question of what is life, and I hope that is the case. But given the data that we currently have, life works in service to creating more heat in the universe, to creating more entropy in the universe. And it does so, to get technical for a minute, by harnessing the Gibbs free energy in predominantly chemical reactions that are available in the environment.
Delta G. I remember this
Delta
too.
G, yeah. So,
Some bowling ball rolling down the hill.
well, so let me give you an analogy that I love to use, which I think
All right.
is pretty intuitive. Uh, you go into a convenience store, caveat with your face mask and
And gloves. Yeah. Your hand sanitizer.
right,
Yeah.
Purell at hand. And you get some batteries, some double A's or whatever for your flashlight. When the apocalypse hits, we're not going to have any power, so you want to get your batteries. Um, you now have those batteries, and there's a bunch of stored energy in those batteries. If you just leave those batteries in your cabinet, eventually the little electrons will go along the surface of the battery, and the stored energy will dissipate as the positive and negative terminal come to equilibrium because of the slight drift of a minuscule current across the battery. And
right. It'll take a really long time, but it'll happen.
that's right. And that date is on the batteries, and yeah, it takes a long time. Meanwhile, If you open that battery pack and put them in your flashlight and turn on your flashlight, now the energy in those batteries gets dissipated, it gets used a lot faster. But in the process, you're getting something done. You're getting some work out of that flashlight. You're getting some light out of that flashlight. And that is ultimately what biology does, what life does. We are the circuit. We are like the flashlight connecting the positive and negative terminals on a host of different geochemical batteries that exist out there in nature.
So is there though like a tautology or like is there an assumption in this definition that like the sun, for example, is not alive, even though the sun is accelerating this as well, or that like some sort of volcanic process is not alive, or the wind, for example, something as simple as the wind is accelerating entropy in a way, but the wind is not alive because it's what would happen anyway.
Right. So there's, there's lots of different layers in this. So, what I've just described is life as a process. It is one type of a process that alleviates chemical disequilibrium in the environment and accelerates or helps with the second law of thermodynamics. What you've just described, stars and the atmosphere, et cetera, are great examples of other processes that also work in service to the second law of thermodynamics, increasing entropy. But they are atmospheric or geologic or stellar processes. Biology and life is a self-replicating, to use the sort of textbook definition, is a self-contained, self-replicating system capable of genetic mutation that undergoes Darwinian selection. Now,
Right. So in
now,
that perspective, a virus is also alive, right?
okay. So first and foremost, I really don't like that textbook definition, um, but it is what you will find in biology texts. And part of what motivates my interest in the search for life elsewhere is the desire to find a second sample through which we can compare the fundamentals of what life is and what life does, and really kind of explore this aspect of compartmentalization and information storage and replication and metabolism. Now, viruses. This is obviously relevant to the universe in which we currently live.
Oh yeah, and it's kind of like an ongoing sort of conflict in biology, right? Like, are they alive? Are they not alive? How do we define them?
Yeah, and when it comes to viruses and this question, I frankly don't concern myself too much of trying to figure out whether a virus is life or not, but rather I focus on some operational definitions for life. And the reason for that is because, as you rightfully mentioned, we can think about tautology and really sort of philosophical boundaries for what life is and what it isn't. But we are in such the early stages of what is hopefully a revolution in biology that I think our tautological efforts are severely constrained. And what I mean by that is the following: imagine you're Joseph Priestley, and you're discovering oxygen as an element, and you're playing around with oxygen. If you have just one element, uh, this is rolling back the clock a few hundred years, you're going to have a hard time with the philosophy of what an element is.
Absolutely. Yeah, it's everything and nothing. It's the only thing you know.
Yeah, and it's really through the development of the pattern of the elements, the periodic table, from which Mendeleev and others were able to kind of systematically see the relationship that then allowed us to truly understand what an element is, how it fits with the atomic theory of matter, and so on and so forth. When it comes to biology and life, and so Joseph Priestley and others in the early days of chemistry, they really had to operate with they moved forward with an operational definition of an element. And what I mean by that was it was something that they could isolate in a given reaction by, splitting apart water through electrolysis to fill a bag with what eventually became known as oxygen, and another bag that eventually became known as hydrogen. We right now, at our point in the history of biology as a science, just have one data point. For all of the diversity of life on Earth, we are all connected by the same genetic tree. And so really what I look for is an operational definition of life. What can I look for that will give me signs of life beyond Earth and begin to allow us to assemble that sort of periodic table for life, which brings us back to viruses. So,
Works.
so were I to go to Mars or Europa or Enceladus or Titan and find a complex molecule sheathed in something that was akin to a virus, and important caveat here, and I was able to say that it was definitively not contamination from the spacecraft and carried from Earth. If we truly found a virus beyond Earth, I would see that as a sign of life beyond Earth.
Is that because it would imply that it had infected something at some point, or is it because on its own you would consider that to be a sign of life?
Well, let me give you another analogy. And this analogy is imperfect for a couple of different reasons that we can go into, but it works. Let's imagine that you're walking along the street, again, mask, gloves, etc., and you find a USB stick. And you are able, without plugging into a computer, to see that it's got some software on it. What would you conclude about let's say you were, off in the Atacama Desert, and you just stumbled upon a USB stick? What would come to mind with regard to the implications of finding that USB stick?
Somebody was there before me and dropped a USB stick.
And that person probably had a computer because they were using it right. So the USB stick implies a computer. A virus is kind of like a USB stick in that it's this little capsule that's got some software in it, and you plug it in to biology, and it's off to the races, and you've now essentially biologically downloaded that virus. And that, of course, is why we talk about certain software as being viruses, and we have concerns about plugging a random USB stick into our computers.
Yeah, but it can't exist without that partnership with life.
That's right.
At least as far as we understand it.
That's right.
Because it also uses some of the same basic ingredients as life.
That's right. So we would have found the software of some alien life form. Now, would I be satisfied? Would I be like, oh, cool, we found a virus, end of story? No, because really I want to understand the biochemistry and see the beauty of that life.
But the cool thing is that a virus would actually give you way more information than no virus. It would be like a way, like a stepping stone, because it would tell you about especially if it had already infected something, and injected its own DNA and maybe taken up some DNA. It would tell you something about the kind of fundamental, I don't know,
code
Duh,
and
structure.
yep.
Yeah, exactly. I was about to say design, and I caught myself. Don't
Very
like
good.
that word.
Good, good.
Very confusing. Okay, all right, I'm digging it. I like it. So gosh, it's like we've already been going longer than an hour, and there's a million other things that I want to ask you. So I'm going to try and like rapid fire some of these, even though I doubt that they give rise to rapid fire answers. But I
I'll
don't
do
want
my
to keep you
best.
all night because you have to go to work tomorrow, or you have to work from home tomorrow, I should
Yeah.
say. So, okay, quick one that I've just come up with on the fly. When I think about my education, which is limited in this kind of area, but I do have a bio degree that was mostly focused on neuroscience. I remember learning a lot about the Miller-Urey experiment, and I remember thinking about like what did they call it, like abiogenesis, or like this idea of like how did life actually form? How did we go from like certain types of molecules, which we know are building blocks of life, like we think you know, I think we've actually found on Mars. Am I wrong? Anyway,
Uh,
that's a side note. But how do we go from this idea of like things that are required for life but are not life into themselves to making that leap to life? Do we know? Maybe we don't know that well, but what is the kind of like general consensus in the field? And did Miller-Urey contribute to that at all?
Right, right. So, in an effort to stick to your request to rapid fire, um,
Let's talk about this for 3 more hours.
you'll have to pardon my plug here. But if you read the book, there's I go into this in some detail.
Oh, you
But
do? Oh,
yeah,
good.
and
Okay.
so the Miller-Urey experiment was sort of the key. Uh, Experiment that catalyzed a lot of the modern epic of understanding from an experimental standpoint the pathways to the origin of life. And so what they showed is that you could cook up some basic molecules like water and methane and ammonia and get to amino acids.
With like lightning or something? Like you just need
Yeah,
an
spark
energy source?
discharge, lightning
Yeah,
was the
okay.
analogy on Earth, and we can do that under a number of different conditions. I've done some similar stuff in my lab with ices, etc. But
Oh, cool.
uh, as amazing as the Miller-Urey experiments were, they got us to a certain point in kind of abiotic synthesis of things like amino acids, but then the field hit a bottleneck. How do you actually get these amino
Oh,
acids to link together? How do you get
right.
nucleobases to link together?
So it
And
got us to building blocks only. It got us from basic chemistry to building blocks of life, but then where does life still come from?
that's right. And so this is part of
Okay.
the sort of bottom up problem that we have in the origin of life is you can get some of these, simple molecules pretty easily, but you can't jump all the way to a polynucleic acid or an RNA that would then jumpstart the RNA world. So that's the bottom up side is things like Miller-Urey's experiment, and then the top down is we can take apart life as we know it and get to the minimal genome and various things, and we can look at molecules like RNA and say, hey, look, a lot of the software is here in RNA, such that if you got to an RNA molecule, then it was off to the races. But there's that gap between the bottom up approach and the top down approach that we still
And
have yet to solve.
is RNA it? Is that the step that people are just like, man, if only we could figure out RNA?
That's right. If you can get to RNA
Yeah. Okay.
or in some simpler derivatives, polynucleic acid of some form, then there's good reason to think that you can get uh, um, through to DNA and life as we know it.
And then we're talking like super super simple bacteria with just like these nucleics just floating in them, nothing else going on.
And
But
you got a horizontal gene transfer and a
yeah,
bunch of that stuff. Yep,
but we still got to get there, right? Like we
that's
got
right.
to get because we get how things continue to organize. We've seen it. Like we can
Yep,
experimentally induce it, and we can, compare simpler organisms to more complex organisms and see what was happening evolutionarily. But this isn't a function of Darwinian evolution. This is something that was like a precursor to evolution.
that's right. And that's where here again we can do this experiment. We can go out to these worlds like Europa and Celadus and Titan and see whether or not life has arisen on these worlds. And they've had the opportunity, and Mars also, to rerun this experiment and see whether or not there's sort of a convergence biochemically or a contingency biochemically the origin of life and what it leads to, DNA or some other biochemistry, or nothing at all.
Mm-hmm. So okay. I don't know if you remember, like an hour ago, when we were starting our conversation, we went off on a bit of a tangent, which became the whole interview, which I'm very excited about. Where I was asking you about how you got to be an astrobiologist. And we talked first about your studying chemistry and physics and psychology. And then we never quite got to what you did after that, which is so important for the kind of experimental work that you do in your lab and in the field. So what was your so those were your undergrad degrees. What was your master's in?
Yeah, so after undergrad, I went and I worked at the NASA Ames Research Center for a year and a half. And then I went back to school at Stanford and got a master's in mechanical engineering and robotics. And that was just a fantastic experience I love building things and tinkering. And so that was kind of in the early days of what were at the time were called embedded systems. This is before Arduinos and DIY and all that stuff really was everywhere. Um, but it was an exciting time to be working on robotics. And
And of course
then
those robots, help out with the work that you do now. But before you got to do, run your lab and do the work that you do now, you did your PhD in what?
right, so then I did my PhD at Stanford in the department of what at the time was geological environmental sciences, and I was working with a professor who was there at the time, Christopher Scheibe, on Europa. So I did my Europa.
Uh,
I did my Europa. I did my PhD on the physics and chemistry of Europa's surface and subsurface ocean.
well, shit. So that's been the guiding for. I mean, you at that point were already focusing in on what you wanted to do for your entire academic career.
Yeah, I got hooked on Europa back in 1997, roughly, when a bunch of the news articles and graphics from NASA were first starting to come out about the subsurface ocean. I was too young to be a part of the Galileo mission, and but back then there was an image of a melt probe going through the ice of Europa and getting into the ocean and looking at hydrothermal vents. And yeah, that's basically been the guiding light for me ever since.
Ugh, and so now you have this lab at NASA's JPL called the Ocean Worlds Lab, which I love, and you're doing like a lot of cool chemistry in the lab to try and simulate or replicate these different environments. But you're also doing a lot of field work, right?
Correct. Yeah, and a lot of that field work is in an effort to understand the extremes of life on Earth in icy environments and deep ocean environments, trying to just uh, really understand the pressure, temperature, pH, chemistry conditions that set the bounds for habitability. And that's great because it also helps expand our understanding of our own biosphere. But coupled with that science, one of the things that I really enjoy and think is incredibly valuable in our fieldwork efforts is that we're also developing a tremendous number of new instruments and new robotic platforms that have as kind of the long-term vision searching for life on Europa or Enceladus and exploring the oceans there. But in the near term, they're really helping to, in some ways, transform how we explore our own ocean. And hopefully, they're opening up whole new vistas for exploration in the deepest regions of our ocean and in some of the coldest, iciest, hardest to access regions of our ocean. And frankly, some of the regions that are experiencing some of the biggest changes due to climate change and warming temperatures near the poles. So our team is building robots that roll on the underside of the ice and uh, CubeSat type vehicles that are going into the ocean to get down into the hadal trenches, the deepest trenches in our ocean. And it's a great merger of ocean technologies with space technologies.
Oh, I love that. And it also, I think, really kind of encapsulates what a lot of JPL's mission has always been, I don't know, always, but has been for quite a long time, which is these robotic, kind of uncrewed, like we can do so much more. And that's not to denigrate crewed missions, and it's not to even open up a conversation about why should people go here or there, but really it's a whole other type of space exploration that you can do farther in more extreme environments when you're sending machines instead of human beings.
That's right, and there's a very interesting parallel here with the evolution of our capabilities to explore Mars. Uh, Long before the Curiosity rover ever landed on Mars, long before even the exploration rovers or Pathfinder landed, we had to figure out, and I say we, this was before I came into existence, um, but the scientific community, the engineering community, had to figure out how to uh, study desert environments on Earth that were kind of analogous to what was expected on the surface of Mars. And so, Pathfinder is a great example, and Mir is a great example. Steve Squires, who was the PI of the Mir rovers, brought teams and then prototype rovers out into the Mojave and elsewhere to figure out how to get science done on Mars. And in so doing, those teams also did a lot of great work, geology work, in deserts around planet Earth. When it comes to alien oceans, when it comes to these liquid water environments beyond Earth, like Europa, uh, we have this beautiful potential for a win-win where to explore and study those worlds, we need to develop tools and technologies that can operate in icy environments, in deep liquid water environments. And the best place for us to develop those tools and test them out is in our own ocean. And it just so happens that, of course, at this point in time, at this point in the history of humanity, there is no more important thing to study than our own ocean. Our planet is changing rapidly, and we need to get more instrumentation, more robotic vehicles, more systems into our ocean that can collect the data that we need to better understand what's happening on our home planet. So there's this really nice win-win that inspires me with the work that I do on planet Earth, and serves as a bridge to these oceans beyond Earth.
I love it. And I mean, it's not only are there certain places on our planet and certain areas of our ocean that are really kind of brutally inhospitable, like similar to these ocean worlds that you might be visiting, but also like pretty, I guess, as far as sort of from an exploration perspective, still pretty unknown. And so you're going to some of these really extreme places, right? The Arctic, like Antarctica, like deep, like the deepest parts of the ocean to look at these hydrothermal vents.
Yeah, and here again, it's when you look at the history of exploration in these environments, a lot of it has been made possible by humans traveling to those environments and um, and studying those environments directly. And again, so the last chapter of my book goes into detail on this, and I make some comparisons on how ocean exploration is done and how space exploration is done. But for the most part, when you look at the history of ocean exploration, it has been enabled by ships and other capabilities um, handed down from the Navy. So a lot of the research vessels historically were formerly Navy ships. Why is that interesting and important? Well, Navy ships are huge and very capable. And so the oceanographic community was able to bring humans out to the ocean, to bring large human submersibles, to bring large robotic vehicles that have massive tethers, etc. And so the evolution of technology that's been used to explore our ocean is kind of a brute force, a story of brute force technologies.
Right, right. Big and
Meanwhile,
and harsh.
Yeah, and
Yeah.
a lot of the kind of foundational samples and experiments that were done in Earth's ocean involve dredging, which you can't really do much these days, thankfully. But you would just essentially drop a bucket and drag it along the bottom of the ocean and pull it up and see what you gathered, because that was the only way you could do it.
Right, but
So
now you wanna do, like, in situ work. You wanna see how things are happening where they're happening.
exactly, and that is how the space community has long operated. We don't have the option of sending humans to all these different places from which we need to get data and science. And on top of that, we don't even typically have the opportunity for sample return.
Yeah.
And
You have to analyze it in place.
we got to analyze it in place. And there again, it's interesting doing the compare and contrast with the oceanographic community. Not only do ships traditionally go out to places and deploy large systems, but then you bring those samples, rocks, water, biology, etc., onto the ship, and then you bring them back to your lab, which is at whatever university you're at. And again, a tremendous amount of great science is done in that realm, but it's a completely different mode of operation from how our NASA missions operate, where you do the science, like you were saying, in situ. We send a rover to Mars that's got a spectrometer on it that looks directly at a rock and sends that data back to us, and then we figure out what that rock was made of. And the only thing that ever traveled back to us was a bunch of zeros and ones tapped out on an antenna. Um, and so part of what we're trying to do in some of the projects that me and my team are leading, and I've got a associate position at the Woods Hole Oceanographic Institution, and JPL and Woods Hole are working on some of these vehicles together. Part of what we're trying to do is break the mold on how ocean exploration is done. And we're trying to take some of these in situ technologies, some of these technologies that enable autonomy and sampling and mapping and all these other things. We're trying to leverage what's been invested for space exploration and apply it in our ocean.
I love that. And of course, like, not only are you doing all of these things and continuing to develop means to do these things in our own ocean, but you are working on a lot of missions and mission concepts. Like, you're working on Clipper right now, Dragonfly. You also talked a bit, and we didn't even really get to get into it, but hopefully we can do a round two about the Europa lander mission concept. But what I want to know from you is, like, if there were no constraints, and I don't mean scientific constraints, because that's a little bit different. Like, we have to operate within kind of a realm of possibility, but let's suspend probability in terms of budgetary constraints, administrative, bureaucratic constraints, things like that. If you could really fantasize about what type of science you would want to do on one of these ocean worlds, what would you be looking for? What would you be actually engaging in?
Yeah, so the Europa lander mission concept is a good example of kind of the next step that many of us would love to take, where you get down to the surface of Europa and scoop up a sample and look for complex organics that could be indicative of life. You look perhaps with a microscope for structures, compartments that might be indicative of life. You look for things like amino acids and the possibility of things like chirality, a handedness to the compounds as an indication of life. And what's exciting about missions that would go to the surface of Europa or go to the surface of Enceladus or fly through the plumes of Enceladus or like Dragonfly will get down to the surface of Titan is that none of these missions requires a technological magic wand. Um, you don't need warp drive. You don't need to invent warp drive to get to the surface of Europa. We know how to do it. we're only limited, frankly, by the scientific will.
And the
Recently,
money, but I guess that's part of the will,
well,
right?
we had the money for a while, and I won't get into it too much, but for your listeners out there, we're coming up on a decadal survey, a big survey of the science priorities for the next decade that the NASA planetary science and astrobiology community will undertake. And the public, the taxpayers, we work in service to the taxpayers. And so, I encourage folks to get involved and look at the National Academy of Sciences Decadal Survey website and voice your opinions and thoughts about where you want us to go and what big science questions you want us to undertake.
Right on. Yeah.
There's a lot of great stuff out there, and I hope we can do. I hope we have a robust enough budget in the future that we can advance the frontier along many different efforts, getting not just to the surface of Europa, but also flying through the plumes of Enceladus, getting back down to the surface of Venus, flying out around or past Uranus and Neptune, of course, getting back to Mars. Um, these days, NASA operates on a small fraction of the budget that it had back in the 60s and early 70s. And I think the public is hungry for great exploration. I think the public is excited for inspiration and discoveries and great science on Earth and beyond Earth. And goodness knows we could use some of that these days.
Yeah, and in many ways, it's so interesting that not every aspect of the type of science that is done at NASA, but above all, just this idea of understanding things beyond our world, both within our world, but mostly I would say beyond our world. There's something really cool about the type of science. Again, not all of it, but most of the type of science that's done at NASA that is really like bipartisan in nature. Like people from all walks of life are very excited about, like you said, exploration, inspiration, learning more about the universe in which we dwell. And that's always been really, I think, cool about NASA is that it almost doesn't matter. There are changes based on different administrations, but it almost doesn't matter what the party our president or our Congress is in. People care about this across the political spectrum.
It's a very unifying endeavor. Um, and as somebody who works at JPL, I feel very fortunate that we have that kind of support. And I'm grateful to all your listeners and the taxpayers who make it possible.
Absolutely. Well, so, I've been talking to you for an hour and a half and it's late and you have to work in the morning. Before I always ask the same two questions when I close out my podcast, but before I ask you those, is there anything that we didn't really cover or anything that you feel like you want to make sure that, the people listening right now know, before they pick up your book, which you guys go buy the book. Come on. What are you doing?
No, a lot of what we didn't cover is in the book, and so if you enjoyed what Cara and I talked about, I think you'll enjoy the book. And thanks for listening.
Yeah, good. Okay, so obviously, I close my episodes by asking people the same two questions, and they're big picture questions, and I really want you to be able to answer in whatever context is relevant to you. We're living in a weird time. Whether that influences your answer or not, that's up to you. And I think now might be another time to reiterate what I said in the intro, which is that Kevin Hand's views are not representative of the views of NASA or the Jet Propulsion Lab or Caltech or the federal government. Because, I don't know how you're going to go with this, but I'd love to hear your honest answer. So here it is. When you think about the future, I want to know, what is the thing that's keeping you up the most at night, that you're most concerned, maybe even pessimistic, even borderline cynical about, what's not looking good. And on the flip side of that, what are you truly optimistic about, like honestly and authentically optimistic about?
Yeah, great questions. Obviously, given the COVID-19 situation that we're in, that's a tremendous concern. I did do some work on bioterrorism and various other aspects of the policy associated with bioterrorism and nuclear materials many years ago, and we will get through this. I think we're going to learn a lot of tremendously useful lessons. It was only a matter of time until something like this happened. And as tragic as it is, in some ways, hopefully we will come through it on the other side with a lot of lessons learned. But really, what does keep me up at night is has more to do with the future of energy, and for the love of God, just getting humans off of our oil habit and onto a truly technologically sustainable energy future with solar, wind, geothermal, potentially fission and fusion, etc. There is, and many other people have written about this brilliantly, but if we don't, so in order to build that future, we need the current oil and gas inventory that we have. And if we drink up and use all of that oil and gas without building the infrastructure and the capabilities for that future, the technologically advanced civilization that we have here on Earth is going to be relatively short-lived. And we will not someday join the galactic club.
Yeah.
But then what keeps me optimistic? I don't know. I guess talking with my nieces, I've got a beautiful smattering of young nieces who are much smarter than I was at their age, and so creative and so inventive. And I love just spoiling them with science kits and various various toys, and they send me drawings and various videos of them doing experiments. So it's cliched, but the youth and what I see in terms of the ingenuity of the next generation and the energy that the next generation brings to the staleness of the older generations.
Oh, absolutely. And just kind of the I don't know, sophistication with regards to like the ways of the world. I'll tell you, I was not politically informed until like college, like maybe late high school, but honestly, mostly I started to develop really strong political ideas probably in like early college. And I know kids now that are in middle school who, if they could vote,
Yeah.
I wish they would.
Yeah, absolutely.
It's amazing. I'm so right there with you.
Yeah.
Well, gosh, Kevin, I learned so much in this episode. I feel like there's still so much yet to learn. So, everybody listening, I really do hope that you will pick up Kevin's new book, Alien Oceans: The Search for Life in the Depths of Space. It's on sale, I think today that this podcast airs, as of like today or tomorrow or something. So you could definitely go and buy it right now. Kevin, thank you so much for joining me. It was amazing.
Thanks so much, Cara, and stay safe and healthy.
Absolutely. I'm working on it. And everybody listening, you stay safe and healthy. And I'm looking forward to the next time we all get together to talk nerdy.